Hi everybody, in this video we're going to talk more about the properties of exponents. As I mentioned in a previous video, there's quite a few of them. So in this video we're going to talk specifically about division. So we're going to look at the quotient rule, and then we're also going to look at what happens when you have an exponent that is zero or a negative exponent. So let's start with division in the quotient rule first. Okay. So here is our quotient rule. It says if m and n are positive integers and a is a real number, so is real, so a real number, but a is not zero, then we have the following rule. So if we are dividing with the same base, so both of those have base a, then what you can do, the shortcut is to just subtract the exponents. Okay? And again, this is a shortcut rule. So all your exponent rules or all these properties of exponents are just shortcuts. You can always go back to the original definitions of an exponent to actually get answers as well. But hopefully these rules, although they take a little bit of time to memorize, will help you to get through the problems faster. Okay, so the big thing to notice here again is you have division here. So it's like a fraction, but you have the same base on top and bottom. So let's look at a few examples. Let's do 3. And all of these are going to be to simplify. So let's do something like x to the 6th over x to the 4th. Notice that you're dividing here, you have the same base, and they have exponents. So what the shortcut says is we just take our exponents and subtract them. Now it is really important when you subtract, you always do the top minus the bottom. If you do it the other way, you're going to get the wrong sign and your answer is going to be wrong. So it's really important to just be careful with that subtraction and go top minus bottom. And I'll show you why it actually works. So if you think about x to the 6th and x to the 4th, x to the 6th means that we have 6 x's being multiplied together. And x to the 4th means that we have 4 x's being multiplied together. So if you think about canceling and simplifying fractions and things like that, well, we can cancel pairs of factors on the numerator and denominator. So that pair of x's cancels, this pair cancels, this cancels, and this cancels. And the reason each of these individually cancel is because when we divide the same thing by itself, we get the result of 1. So x divided by x is just 1. And multiplying through doesn't change anything. And notice what I have left over. I have those 2 x's left, which is just x squared. So you can see that the shortcut rule doesn't actually change our original definitions or original strategies. It still builds on all those rules we already have. It just provides us a shortcut. All right, let's do a couple more examples. So here I have 4 to the 8th divided by 4 to the 2nd. Now I am using numbers here, but because they are the same base with exponents, it's still fine. So my base in both cases is 4. And then I subtract top minus bottom. So this becomes 4 to the 6th. Now, if I wanted to go ahead and multiply that out, I could. So this is one where it's pretty large, so I would definitely get my calculator out here. So here I just have one of my apps, And there's different ways to do this we've talked about, but if you have the TI 83 or 84 series, you're gonna see a little up arrow on your calculator there, and that's your exponent. So I could do 4, and then I hit that little up arrow, and I'm gonna just type in 6, and then I'll hit enter. So I get 4,096. If you have a more traditional calculator, so let me bring up my regular one. Okay. Sorry about that, everybody. So here, let's try a more standard calculator. So this is just another app I have on my phone. It's the standard app that comes with an iPhone. And what you do is if you just turn your iPhone to the side, then more keys will open up. So your exponent is going to be this one right here, this x to the y, or sometimes you'll see it as y to the x. It's the same thing if you have a different style calculator. So I just hit that 4, and then I'm going to hit my x to the y key. I'll hit 6 for my exponent, and then I'll hit enter or equals, and I get that 4,096 that way. So let's kick it up a little bit here. Now I'm bringing in a couple of different variables. So what I'm going to do here is I can only apply the shortcut rule to variables that match, that have the same base. So I'm going to go ahead and do that. So now here I have a 2 out front and I have nothing to match it with. So I'm just going to leave that 2 for now. It's in the numerator, so I'm just going to leave it in the numerator. And then I'm going to go ahead and I'm going to match up my x's because those are the same base. So I have x, and I always do top minus bottom. So 4 minus 2. And then I'm going to go ahead and match up my y's. Now remember, if there's no exponent, there is a 1 there. So this is going to be y to the 2 minus 1. Now I can go ahead and simplify. I don't have anything to do with the 2. I'm just going to leave it. 4 minus 2 is 2. 2 minus 1 is 1. Or again, we don't really need those exponents of 1. So I can simplify a little bit further here. Notice that once I do the subtraction, the value is automatically in the numerator. So that's really important to notice that maybe it wasn't as noticeable in the first two, but here once we start getting into multiple variables, it seems to be more obvious that once you do your subtraction, again, that x is going to be up top or that y is going to be up top. It's no longer in the denominator. Oops. I just want to do another example or two. All right, so again, here's another example. Okay, so again, I'm going to match things up. Now, I do want to be careful here. So notice that I have a 4 and a 2. Now, that 4 over 2, there are no exponents. And this is not the same base, right? So this is just a regular old fraction that you will simplify, okay? So if you think about 4 over 2, well, 4 over 2 simplifies to just 2, right? 4 divided by 2 is 2. So if you have just numbers out front and there's no exponents that are going along with them, we can't use that shortcut. So we're just going to divide here as usual. 4 divided by 2 is 2. And then I'll match up the other parts. So I'll do my a's next. So this first part just becomes 2. And I have a to the 8 minus 7. Now I'm going to do those b's. And again, there is a 1 there if you need to write it in. So b to the 2 minus 1. Use all my different colors here, make a little rainbow. And then I have c to the 4. Again, there is a 1 there, so minus 1. This becomes 2a to the first power, b to the first power, c to the third power. And again, we don't really need those powers of 1. They don't really make a difference there, right? They're just telling us we only have one of that variable, so I can simplify. Again, I'm just going to do one more example here. So again, those numbers out front, you just want to be careful. I don't have any exponents here. There's nothing, no similar base. This is just a regular fraction. So I take that 4 over 12 and I'm going to simplify it. Now I can't just divide here because the 12 is bigger and it's in the denominator, but I can simplify. So I can divide these both by 4 over 4, and then I get the value of 1/12. So do want to be careful. It's not just, sorry, not 12. Oh my goodness, 1/3. So we don't just want to have the value of 3 here. It's 1 over 3. Remember, if the 1 is in the numerator, you have to leave it. So this becomes 1/3. And then I have the x's next. So if I look at my x's, I have 5 minus 3. And if I have my y's, I have 3 minus, and again, there'd be a 1 there. So this becomes 1/3 x squared y squared. Now this is actually fine, so you can leave your answer like this. Or if you wanted, you could kind of multiply this through. Just be careful, fractions multiply straight across. So what this also would look like is 1x squared y squared all over 3, because the only thing in the denominator is a 3 there. These would both have 1s. And then again, we don't need to multiply by 1 here, so you can rewrite it as this. So this is correct, and this is also correct. They're both perfectly fine ways to write that final answer. Now, sometimes, I'm going to go to a new page for this. When I'm doing this quotient rule in particular, I may end up with a 0 exponent. So for example, let's say I have x to the 3rd power over x to the 3rd power. So when I go to use my quotient rule and I subtract, I end up with x to the 3 minus 3, which is x to the 0 power. So how do I deal with that? And what ends up happening here is that anything to the 0 power, as long as a is not 0, is equal to 1. And again, but a is not 0. So for instance, in our example then, x to the 0 power is going to be the value 1. Now, why does this work? So let me show you why this works. If I have x to the 3rd over x to the 3rd, and I write this out, I have x times x times x over x times x times x, right? So what ends up happening here is you cancel these one at a time, right? These all cancel. But when we're doing division, when things cancel, when I have the same thing on top and the same thing on bottom, and I divide them, the value is 1. So that's why our answer here is 1. Okay? Think about if I have something like 5 squared over 5 squared. Now, when I use my exponent rule, I get 5 to the 0 power. But I also know that 5 squared is equal to 25, and 25 divided by 25 is 1. So these things have to match. They have to go together. I can't have it being the value 1 here, but not here, right? Everything has to connect. So these must be the same answer then. So 5 to the 0 power has to be 1. Okay, so what we're seeing here is that anything to the 0 power equals 1. Now you still have to be a little bit careful in more complicated examples. So let's do a couple different examples here so you can kind of see. And do some examples in blue. So let's say I have 3 to the 0. Right, so it's just a number to the 0 power. Again, the only thing is that number can't be 0. It gets a little bit weird if you have 0 to the 0 power. So 3 to the 0 power is just 1. Or y to the 0 power is just 1. Now, negative 2 to the 0 power is also 1. Notice that I have parentheses here, right? So because I have parentheses, the whole thing is raised to the 0 power or 0 exponent. So that's really important. If I have something like negative 2 to the 0 power, well, this is a little bit different because this part here is 1, but that negative is not part of the exponent. It's just like when we're squaring things with negatives, right? We have to be a little bit careful. So it's the same thing here. So this becomes negative 1. So anything to the 0 power is 1, but we have to be careful in more complicated problems because maybe not everything is actually going to the 0 power. So let's do another example. Let's say I have parentheses around something like this. Again, everything is to the 0 power. The whole thing is parentheses. So the whole thing is going to the 0 power. It doesn't matter how complicated it is. It's still just 1. But if I have something a little bit different, so maybe I have something like 5y to the 0 power. Now we have to be careful because this is to the 0 power. That's 1. So this becomes 5 times 1, which is 5. Or maybe I have 2x to the 5th, y to the 0. I'm kind of tweaking this one right here. So in this case, that y to the 0 is 1, but everything else is not, right? That 0 is only going with the y. So this becomes 2x to the 5th times 1, which is just 2x to the 5th. Now, I do want to get used to writing in if I'm multiplying something by 1, because again, if you have more complicated problems, perhaps this one actually could come into play here. So maybe I have something like x to the 0 over 4. So what happens is that x to the 0 is 1, but I still have to leave the 4 in, right? So you do want to kind of get used to putting that 1 in and just seeing how it plays out as you either multiply through or simplify. So just be careful. I do like to put that 1 in. You may be saying, well, why are you doing that? You're just multiplying by 1. It doesn't make a difference. Most times it doesn't, but sometimes it may, right? If I have the 1 here, I do need that 1 in the numerator. I can't just have that 4 hanging down in the denominator by itself. So you do want to get kind of used to just still simplifying with that 1. All right, and the other thing that can happen is we could have a negative exponent. So for example, let's say I'm using that quotient rule. And I go to simplify. And remember, it's always top minus bottom. Be really careful there. Students make that mistake all the time. It's 7 minus 9, which is negative 2. Okay, so I'm be careful there. A lot of times students will just write 2, but it's really top minus bottom. So I have a negative exponent. What do I do with a negative exponent? Okay, so a negative exponent actually sort of refers to a reciprocal or flipping idea. Okay, so again, if a is a real number that's not 0, and n is an integer, then a to the negative n is equal to 1 over a to the n, and 1 over a to the negative n is equal to just a to the n. So what we're seeing here is that a negative exponent really means to flip or take the reciprocal. Okay, if we're talking more formal definitions, right? So you can think of it as a flipping action, or in math, we call it a reciprocal when we kind of flip like that. So that's really what it means. And you want to think about this carefully. A lot of students, again, mix these up. You want to think about the zero exponent rule and the negative exponent rule really as definitions. They are rules that exist that fall in line with all of our other exponent rules and also with the definition of exponents and how we simplify fractions and things. So even though they maybe look kind of weird, they still fall in line with everything else. And I kind of showed you that with the zero exponent over here, right? So just doing an example, you can see that, you know, when I use the quotient rule and when I go back to my regular arithmetic, these things have to match. They have to give the same answer. So that's why a 0 power is equal to 1. And here, I'm going to show you why a negative exponent gives you this flipping action. Okay, so let's do an example again. And I'll do the one above. So x to the 7th, I should have chose smaller exponents, that's okay, over x to the 9th. So we need to have 7 x's here. 2, 3, 5, 6, 7. And then here I have 9 being multiplied. And just like before, when we simplify a fraction, we can cancel the same factor in numerator and denominator because it gives you a factor of 1. So I can cancel this pair, I can cancel this pair, this one, this one, this one, this one, and this one, but I have 2 left over. So those 2 left over, notice, happen to be in my denominator here. So they have to stay there. So you have x squared. But I do need something up top. Now remember, all these factors are actually equal to 1, so I can put a 1 there and make that work. And then if I use my rule, we already saw that this is equal to -2, so my rule says that I go ahead and flip this. So I put a 1, and then I flip this to the denominator, and you can see that they match. So our rule here, again, these are all shortcuts, really just are fast ways to deal with exponents, right? So I could write this all out if I want to every single time, but it's just going to take me a lot of work, right? Very tedious work if I have a hard problem. So the shortcut here is really that if you have a negative exponent, really that value should be in the denominator. If your negative exponent is in the denominator, it works the opposite way. So you would flip it back up to the top to kind of fix it and correct it that way and simplify it. All right, let's do a couple more examples. And again, all of these are going to be simplified. I'll just write it one time. So let's simplify something like 2 to the -3. Okay, I see a negative exponent there. It's already in the numerator, right? There's no denominator here. So I'm going to flip it down. Once I flip, it becomes positive. Okay. So once you flip or reciprocate, the exponent becomes positive. Now, if you can't simplify, you would keep going. 2 to the 3rd is a pretty easy one to do, right? It's just 2 times 2 times 2, which is going to be 8. So I get 1/8 for my answer. All right, let's try a couple more. For x to the -3. So here I do have a negative exponent, but be careful that negative exponent is only on the x, right? So just this part is going to flip. The 4 is going to stay where it is. So the 4 is in the numerator, right? Because I have no denominator. So it's in the numerator. So this is going to flip down, and I have this as my final result. If I have something like this, this is different. So notice that the whole thing is to the -3rd power, right? Because I have parentheses here. So it's the whole thing is going to flip. And then I can go ahead and use some of my older rules to go ahead and distribute, right? So I can distribute that 3 to each part here. And then I can go ahead and multiply out and do 4 times 4, which is 16, and times 4 again. Okay, there is. That will give us 64, and then you have your x. Let's do something a little bit different. Let's say I have 2 to the negative 1 plus 3 to the negative 1. Well, each of those negative exponents has to get flipped down. So this becomes 1 over 2 to the 1 plus 1 over 3 to the 1. Now, 2 to the first power is just 2, and 3 to the first power is just 3. So this is actually just a different way that we can write fractions. And do remember that you do need common denominators when we add. So for the first case, we can multiply this first one by 3 over 3. And we can multiply the second one by 2 over 2, and that will give us that denominator of 6 here. So my answer would be 5, 6, which is simple. So again, let's say just part of your piece had a negative exponent, then just this one is going to end up flipping. So what everything else is going to stay where it is. And that would be simplified here. Or let's say I had something like 1 over x to the negative 2 y cubed, right? So now I'm working with denominators, but again, I see I have a negative exponent here, so this time it's going to flip up. So I end up with 1 times x squared over y cubed. Now here I don't need the 1 anymore, so I can rewrite it like this. If I did have a number there, though, let's say I had something like 10 over x negative 2 y cubed. So you just want to be a little bit careful when I flip this up here that I would have that 10, right? So 10x squared over y cubed. So you want to make sure you don't get rid of the number if there's something already there, or if there's a variable there, you're just going to multiply it along with the other values there. Let me just do 1 or 2 more examples, and then that will be the end of the exponent rules. All right, so I'm kicking up a little bit here again. We're actually bringing in 2 steps. So first I'm going to use that quotient rule and rewrite it, subtracting those exponents, and then I'm going to see if I need to apply my negative rule. So I tend to like to save my negative exponents for the end personally and use my other rules first, but you don't have to. I am noticing that I have the same base here being multiplied, being divided, excuse me. So I can go ahead and use that quotient rule and subtract 1 minus negative 2. Now you need to be really careful here. When you subtract, it's always top minus bottom. So I have 1 minus, and then the denominator is negative. So what ends up happening is these 2 negatives will cancel using our sign rules, and we actually get y to the third. That's another common mistake students make, is they'll forget to cancel like that negative here. So they'll just do 1 minus 2 and get negative 1. So you want to be careful. It's always 1 minus whatever your denominator is. All right. I wanted to write that a little bit lower. So x to the negative 4 over x to the positive 7. Sorry about that little mistake there. So again, I'm just going to subtract. So negative 4 minus 7. And you need to use your sign rules here. So I have a negative 4 plus a negative 7 is negative 11. Now, we don't like to write our final answer with negative exponents. Typically speaking, you're going to see problems that say use positive exponents. So what I need to do now with this is I'm going to go ahead and flip that in my final result. So we can see that these rules can really be used all together now, kind of combining them. And there's one more thing I want to point out here too. So just like we have a power of a product rule, we do have a power of a quotient rule. And what that says is that you can distribute that exponent inside as well. So if I have something like a over b to the n, then I can go ahead and distribute that exponent inside. Okay, so just kind of one more little tie-in with the quotient rule here before we totally move on. So for instance, if I have x squared over y to the 4th power, then I can go ahead and still distribute that exponent in. So I'm going to bring it in here, and I'm going to bring it in here. So I have x squared to the 4th, and then on the denominator, I just have y to the 4th. That one's pretty straightforward. And don't forget here that we can go ahead and multiply those double powers. So I have x to the 8th over y to the 4th. So here again, I could go ahead and bring those powers inside. So I have x to the 5th squared, and then I have x to the 8th squared. And again, don't forget those double exponents we've seen before, you can multiply those. So I have x to the 10th over x to the 16th. Now I can use my quotient rule here. 10 minus 16, which is negative 6. And then I can go ahead and get rid of that negative exponent by flipping. So again, you can start to see that these rules can really be combined and put together. And that's really where it gets complicated. I think each rule individually is pretty, I don't want to say easy, but relatively easy to memorize and kind of just go through the procedures. But once we start combining them, it gets to be a little tricky. The other thing too is that you don't always have to follow one step first. So another way I could have done this one is you may have said, well, I see I can do the quotient rule first here because I have the same base, right? Here I didn't have the same base, but here I have the same base. So what you could do is that quotient rule first, which is going to give you negative 3. And then if you take your double powers here and multiply, you get that same negative 6. So many times with our exponent rules too, it doesn't necessarily matter the order in which you use them in, as long as you're careful. So for me, I tend to like to do, my powers first and my multiplying early, and I tend to like to leave my negatives for the end, but you'll find the pattern that works for you too. So I want to stop this video here. I am going to do one more video on the exponent rules and just kind of recap all of them and put them all into one video and do a little bit of a summary.